Hello everyone, welcome to a new video from Quantum Singularity. In today's video we will cover the Quantum Benchmark Initiative released by DARPA. Following the July announcement of the Quantum Benchmarking Initiative, also called QBI, which will benchmark quantum computing applications and algorithms as well as significantly expand our efforts to validate quantum computer hardware progress. DARPA's goal is to determine if it's possible to actually build an industrially useful quantum computer much faster than conventional predictions. Therefore, DARPA is hosting a QBI proposed this day on September 3rd, 2024, for quantum computing companies that believe they are on track to develop an industrial scale, fault-tolerant quantum computer in the near term. The goal of the hybrid in-person and virtual proposed this day is to introduce the quantum computing research and development community to DARPA and the QBI vision and goals, explain the mechanics and milestones of the QBI solicitation, and solicit and reply to questions from attendees. DARPA will also offer individual, brief sidebar discussions in person or virtually with QBI Program Manager Joe Alpeter. Sidebars will be scheduled following the proposed day on September 3rd, in person and also virtually, and on September 4th and September 6th, virtual only both days. The proposed day and sidebar discussions are open to US and international quantum computing companies and organizations. Fault-tolerant quantum computers, if they can be developed, could be transformative for a variety of scientific and industrial applications, Alpeter said. We are eager to hear from and work with an expanded pool of quantum computing firms, both small and large, in the United States and around the world, to determine which approaches show the most promise to success, and then help advance those approaches. The proposed day and private sidebars will give us a chance to hear from you and have a brief discussion about your approach. We especially encourage teams who previously applied for our US 2 QC program to apply for QBI funding, as we anticipate making a larger number of awards under QBI. All this was mentioned by Joe Alpeter. The performers chosen for QBI will focus on one or more of the following efforts, depending on the maturity of their approach and technology. So number 1, developing and describing a utility-scale quantum computer concept, meaning its computational value exceeds its cost, that has a plausible path to realization in the near term. Number 2, developing and describing a robust research and development plan that reduces key risks that a utility-scale quantum computer can be constructed. Number 3, identifying and validating quantum computer applications and algorithms that provide demonstrated utility. And the 4th criteria is working with the government to verify and validate that the utility-scale quantum computer concept can be constructed as designed and operated as intended. The application areas for quantum computing have been defined. So DARPA would also like to measure the actual quantum computing progress. Therefore, with DARPA's quantum benchmarking program, they kicked off with the goal of reinventing the metrics critical to measuring quantum computer progress and applying scientific rigor to often unsubstantiated claims about quantum computing's future promise. Research findings focus on specific applications where quantum computing might make outsized impact over digital supercomputers. Equally important, researchers estimated what size quantum computer is needed to achieve the desired performance and how valuable the computation would be. In the first phase of the program, 8 interdisciplinary teams compiled more than 200 potential applications from which they created 20 candidate benchmarks that could quantify progress in using quantum computers to solve hard computational tasks with economic utility. For the second phase, DARPA selected specific benchmarks for detailed study in 3 broad categories: chemistry, material science, and non-linear differential equations. DARPA then selected 5 teams for the second phase to refine these chosen benchmarks according to rigorous utility-driven criteria, and then expand those benchmarks applications to incorporate the needed information, that it's scalable and robust testing, evaluate real-world utility, and create tools for estimating resources and performance needed to run end-to-end instantiations of the applications on realistic quantum hardware. The preprints describe the team's results in these areas, showing that it is plausible that quantum computers will provide advantage for economically valuable applications in certain chemistry, quantum materials, and material science applications. It is unclear at this point whether any advantage can be achieved for applications in non-linear differential equations. The findings address potential quantum computing applications, not the hardware needs. For the hardware needs, there is actually another program created by DARPA. It is called Underexplored Systems for Utility-Scale Quantum Computing, US2QC. In this program, basically tries to determine if a quantum computer can be built for these applications that we have previously mentioned. So basically to solve real world problems for material science, chemistry, and AI machine learning. So a parallel effort to the Quantum Benchmarking Initiative, the US2QC program, is addressing whether a quantum computer for these quantum applications can actually be built. It is often thought of, but not proven, that quantum computers will have a transformative impact on a variety of scientific and technical disciplines. 2 separate factors make the ultimate impact of quantum computing unclear. The first factor, although a number of algorithms and applications for quantum computers have been suggested, in most cases a rigorous comparison to the best classical alternatives for real-world usage has not been completed. And the second factor, it is unclear whether or if a utility-scale quantum computer, one whose computational value exceeds its costs, can be built, particularly for applications that require fault tolerance. The complexity of a fault-tolerant utility-scale quantum computer could approach or exceed that of a classical supercomputer. Therefore, a verification and a validation effort that demonstrates a utility-scale design is viable. All necessary components and subsystems for the computer can be produced at the required specifications, and all components and subsystems can be successfully integrated would likely be a difficult multi-year process. The primary goal of the US2QC program is to determine if an underexplored approach to quantum computing is capable of achieving utility-scale operation much faster than conventional predictions. Utility scale would actually mean, right, that quantum computers, or the cost of developing quantum computers exceeds, the profit made from quantum computers exceeds the cost of actually developing these quantum computers. And the US2QC will accomplish this goal through rigorous, collaborative, flexible verification and validation performed in parallel with ongoing research and development efforts. Thank you very much for watching the video. Please subscribe and give a like to stay up to date with the latest quantum technology news.